All right, so we're going to continue here now with a confidence interval for sample means. And we're going to put them all together in a bit with another example. So the formula for confidence interval for the mean is, well, I need my point estimate. And our point estimate is X bar. Then we go plus or minus. And now, instead of using a Z, we're going to use a T critical value. So that's my point estimate. T star is the critical value. And finally, the standard error. The standard error is going to be S over square root of N. So critical value and then S over square root of N is the standard error. Which is an approximation, an estimate of SD of X bar, the standard deviation of X bar. So the standard error is just an estimate, right? So even notationally, we could do this. This is SE of X bar. That's what this is. So standard error. And I go notice the situation is still the same. This is the margin of error right here. So again, margin of error. And could we calculate the sample size? And just like we did for proportion, sure can. A little more complicated and a little more hand waving. So we're not going to do it, but you can. Okay. Just for time's sake, we will not. So the critical value for a particular confidence level in students' t distribution is unique to the sample size. So before we listed like, hey, use, if you want a 95% confidence interval, the Z star value is 1.96. You want 90%, it's 1.645, and so on. But there's no such thing here. So every time you're going to have to look up the T critical value. Okay. So we're going to do that right now. For example, what is a T critical value for a 95% confidence interval when the sample size is 50? So I need to come over here to GeoGebra, make sure that I'm in the probability calculator, that I'm choosing students T. And in this case, my sample size is 50, so I need to calculate my degrees of freedom. My degrees of freedom is 50 minus 1, which is 49. Okay. So I need to change this to 49 degrees of freedom. Now, I want a 95% confidence interval. So I have to, again, remember how this is going to work and what the 95 means. That means the middle is 0.95. That also means that what I'm leaving behind is 0.05. And that 0.05 is evenly split. That 0.05 is evenly split between the two ends. So this side is just half of that 0.05, and this side is also half of that amount. Okay, so together we get 100%. So it doesn't matter which side you do. I always like to choose this side because it will come out positive. This side will be the same number, but opposite in value. So I'm going to come over here. And again, this value here is 0.025. The end point is 0.025. I'm clicking to the right. Can you click to the right and then enter? Oh, nope, make this all go away. So I enter for the output as 0.025, right? That's what I'm entering for the output. And now I'm being told what the T critical is. The T critical then is going to be 2.0096. Okay. There's my T critical value. What if I want to do, what is the critical value if I want to do a 95% confidence interval, but the sample size is 30? So, okay, so notice it's the same setup, but now in this case, the degrees of freedom, it's going to be 30 minus 1, 29. So I got 29 degrees of freedom, same. Everything else above is still the same. I'm looking for 0.025 as the end. I just need to change the degrees of freedom to 29. I did that. And of course, this always gets altered. I don't know why, but it does. So I need to enter again the 0.025. Hit return. Hit return one more time, making sure that it's sticking. I don't know. Sometimes things that get to, I don't know. This doesn't work sometimes. So again, 2.0452. I notice that my sample size went down. It was 30. And now the T star value is going up. What T star critical value for 95% when the sample size is 15? So notice I'm decreasing the sample size again. So my degrees of freedom in this case is 15 minus 1, so 14. I got 14 degrees of freedom. So what is the T critical value? So again, I'm going to come over here, 0.02. Let me change first the degrees of freedom. So my degrees of freedom is going to be 14. Well, I think I know why it's doing that. It's adjusting to keep the input the same. All right, so I'm entered 0.025, and then here's my critical value. So what it's giving you, notice the critical value is this number right here, which just separates the upper 0.025 from the rest of the graph. So it's just this point right here. So T critical is 2.1448, and I'm going to just draw this so we can understand what's happening. So I'm going to exaggerate this, but this is 0.025. And then T is 2.1448. And again, if I did go to the other side and said 0.025, this would be negative 2.1448. Okay. And again, notice it's gone up. So look at the progression. At 50, it's just about 2, a little more than 2. At 30, now it's a 2.04. At 15 is 2.14. So it's going up. So as the sample size decreases with the confidence level, the T critical value is increasing. So it's getting wider. So this graph is definitely getting wider, trying to compensate for the schlop in the data. This indicates that the margin of error is also increasing since it's tied to the margin of error, right? The margin of error is this formula, and we're saying as n goes down, T is going up. And you go, if it goes down, is it going down enough? I don't know. It's a good question. Good question. I'm momentarily stumped. Like, which one is going faster? Is this going down faster than this? Huh. I never thought about that. Something for me to explore. So right now I'm saying increasing because it should be increasing to accommodate the slop, but maybe not by much as I thought it would be. Okay. So what is the T critical value for 99% confidence interval? Just to change it when the sample size is 32. So again, just so we have a good visual of this, I'm going to draw my picture. Notice I'm going to draw the same thing no matter what the thing is. I'm not drawing to proportion. I'm drawing so I can draw this. So it's 0.199. So 1 minus 0.99 is 0.01. And what we have here is 0.01 divided by 2, which is 0.005. 5. And so this one's 0.005. Add them all up and you get 1. So what is my t critical value? Again, I will have to use GeoGebra, enter here. And I get 2.9768. Okay, so there's my t star value. All right. So now we're going to create a confidence interval with this. We found the result, for example, 1, the weight of apples to be statistically, no, actually, we did not find it significant. That's an error. For the hypothesis we had, but it's probably statistically significant for the question we didn't ask. So the next question is, if we reject a null hypothesis, let's say we did it the other side. Clearly, if we did it the other direction, the p-value would have been 0, right? So if we had conducted this test, HA mu is less than 150, we found lots of evidence to suggest that not only is the fertilizer not helping, it's actually doing the exact opposite. But by how much? So if let's say that if now with the fertilizer, it definitely isn't 150. So what is the parameter? What does this mean? So that means I'm going to use the formula here. Okay. So I'm going to look over, I have it written down here, but you would have to go back to the first question and find all the values. But I'm going to write them here just to save some time. Don't I keep flipping the paper over. But I got my mean here is, I lost it. Oh, there it is. 105.095 grams. I had my standard deviations from the data to be 7.644 grams. My sample size was 14. So this means my degrees of freedom is going to be 14 minus 1, 13. That's going to be my degrees of freedom. I think I'm pretty good. Can't think of anything else. So now I'm going to start constructing this thing. What I have is 105.095. That's my mean, plus or minus. Then I'm going to go over here and say, okay, it's 7.644 grams divided by the square root, and my sample size is 14. What's missing here is my t critical value, which I need to use GeoGebra for. So I need to enter 13 degrees of freedom. That's great. And that let's see, we're going to do a 95% confidence interval. So that means that this side here is going to be, so again, you have to do this every single time, 0.025. And I see this value is the t critical, 2.1604. Okay. All right. And again, what is the edge? I guess there's no name for this. This is where naming conventions really help. But to calculate, this area, I guess, upper area, you would do 1 minus confidence level and divide this by 2. Right, and that's because that's what I've done to get the 0.025 right here. I took 1 minus the middle, and that gave me the sum of the two sides, divide that by 2 to just give me one side. So there's that little formula right there. And now I'm going to just punch this all in the calculator and see what the results are. And I'm going to use Desmos again. So again, I'm going to enter everything in one shot. So I come over here and type 1.09.095 minus, and then 2.1604, 2.1604 times, and then I'm going to type 7.644 divide by square root of 14. And there is my lower value. And I'm gonna round this to grams, and the other value, I'm gonna just change this to plus. And get my upper value. So what does this say? Well, oh, you know something? I messed up. That's a 5, not a 9. Oh, embarrassment. So this is not right. My upper value is 109.51. And my lower value 100, can we get 0.68 grams. Fantastic. So what does this mean? Well, the old sing song is this. I am 95% confident. And this is a personal probability, by the way. Need to spell correctly. That the mean weight of apples using the new fertilizer is between 100.68 grams and 100.51 grams. So obviously we'll never know what this parameter weight is, what the real weight is, but it gives us an idea that is somewhere between those two values. In either case, it definitely did not do, the fertilizer did not do what we thought it was going to do. All right, let's now move to the next part here and do one complete. Okay, so we're gonna do its example 7. And I'm gonna turn the light. I'm in a dark room again. So engineers are developing a car. And one characteristic they're going to engineer is the ability to go from 0 to 60 miles per hour in 4.2 seconds on average. A prototype car is developed and 8 test runs are performed. A hypothesis test is run to see if there's any evidence that the benchmarks have been met. Okay. All right. So let's just see if we can state the null and alternative. So we're looking for the average, on average, how many seconds can the car do? But here's a way that we can get a null value. This is just a wish. I wish the car to be in the range of 4.2 seconds on average, right? 0 to 60 in 4.2 seconds. So this is just a requirement that we want the car to perform. So that is going to be my null. And by the way, I don't like this question. I did it, but I'm going to tell you in a minute why I don't like it. So I guess I'm assuming that the car is ready to go. So this is really not a good thing to do. That's one thing I don't like it, because we're assuming the car can do it. And then we're trying to find evidence that the car, well, I should say, okay, have this test run to see if there's any evidence that the benchmark has, I'm sorry, big word missing here, has not been met. So this is totally backwards from reality. So not met means that the car is going, it takes longer. right? Because you want to go faster. So faster means that it's going to take less seconds to go from 0 to 60. So the benchmark has not been met, 4.2. So this is kind of a really bizarre engineering approach in that we assume we have met it, and there's any evidence that we have not met it. So this is totally bizarre. And that's what's really done in reality. At the end, I'll kind of mention what should have been done to begin with in this scenario. But we just want to do an example. So here's my data. I do 8 runs, and there's the data. So I'm going to go and again, in that file in GeoGebra, the data is just sitting there. So let's move this out of the way so we can get to it. And there is the 8 values sitting right here. So I'm going to highlight these, select one variable, and I already have it set to QQ plot. So there's my QQ plot. And well, what do you think? Looks pretty good, I think. Yeah. So data seems to come from an approximately normal distribution. So again, if I just create a cheap version of this graph here, just to get an idea, I'm gonna have this dot here, and then boom. So everything just seems to be, you know, about where it should be. So great. What about the sample mean, standard deviation? Again, I'm going to come over here to the summation symbol, sitting right here, and then I'll get my mean. My mean turns out to be 4.9775 seconds, and a standard deviation of, there we go, 0.6436 seconds. Okay, so I got that information, and now I'm going to create my t-statistic. So my t-statistic is just going to be 4.9775 seconds minus the mean, 4.2, 0.6436 over square root of, and again, my sample size is 8. So n is 8. And I'm going to enter all that into the calculator. Decimals calculator. 4.9775 minus 4.2. And notice I'm going to highlight both of those and hit the division keyboard. So that way it knows to take all that and put it in the numerator. Another way of doing it without having to use parentheses. Then I go 0.6436 in division. Then you could hit the square root button. I'm just going to type square root, just going to go faster. And I get my value. My t-score is 3.4168. And again, I'm going to just look at 7.8. I'm going to round at that point. All right, so what's my p-value? So let's figure this out. So I'm going to write down the formality here. What am I after? Oh, I'm trying to figure out the chance that X bar, again, now I'm looking at my direction here. This is my direction, and the alternative is greater than, and what I found was 4.9775. Okay. Then I calculate my t value, and I get 3.416878. And again, the degrees of freedom here. So degrees of freedom, it's going to be 8 minus 1. So that's 7 degrees of freedom that I'm looking at. All right. And now I'm just going to calculate. This is a one-sided test. So I'm just going to calculate back to GeoGebra, get my calculator going, knock this out for now. And it looks like I'm going greater again, so I have the right button. And I enter, I need to change my degrees of freedom to 7. That's the thing, always remember to change your degrees of freedom. And I got 3.416878. Okay. 3.41. Hit return, and I get 0.0056. And that is very, very, very small, right? This is less than 1%. Right, so this is less than 1%. So yeah, this is very small. So, we found evidence that our prototype car cannot meet our standard of 0 miles per hour to 60 miles per hour in 4.2 seconds on average. So again, we reject the null hypothesis. I mean, so this is totally backwards. Never do you assume what you're trying to prove, but hey, have a little fun. All right. So here's what should have been done to begin with. You should have just created a confidence interval. Okay. So let's create a confidence interval instead. When you have the situation, sure, you have the standard you're trying to meet. That's all fine and good. But we don't need to do a hypothesis test to do this. We know our standard. We cannot set the null hypothesis as the standard. I mean, again, this is just illogical. Doesn't make sense to assume what you're trying to hopefully develop. So I'm using this as an example of what not to do, the reality of the situation. So instead, you should just do a confidence interval. That's it. So we should have done this right from the start, not messed around. And so now I'm going to grab all the information. I'm seeing it. I know it's out of camera, but you have it in front of you. So I'm going to use a confidence interval. And again, the formula, I'm going to just put it right here just so we have something to look at together. But there's my formula. So now it's a matter of filling all this other information out. Okay. 4.9975 plus or minus, and again, now the T critical is something, which I don't know what it is, but 0.6436 was the standard deviation from our data, and the sample size was 8. So divide by that. Now I need to find this value. It's T critical. So over here, we're doing a 99% confidence interval. So again, just remember this, these sides are going to be 1 minus 0.99 divided by 2. So if we did this, it turns out to be 0.005. Okay, so that means I need to go to GeoGebra. And what are my degrees of freedom? Well, it was 7, and I left it at 7, so we're happy there. But I need to enter here this endpoint. Come on. 0.005. And I get my T critical, which is 3.4995. 3.495. So again, when I come over here, and if this is a T distribution, then this value is negative 3.4995, and this value over here is positive 3.4995. And now we're going to just dump this into GeoGebra. and see what we get. Well, I'm going to dump it into decimals. So, let me grab, nope. Something. Kind of cheap out here. I don't know why. Just a little bit of typing. So I got that minus 3.4, not, no, 995, 4995, and then times 0.6436 divided by square root of 8. And doesn't like something, oh yeah, 3.4, not. Yep. All right, so I get my lower value of, I'm going to approximate this, seconds, and my upper value okay. And now I'm looking at this and I go, wait a minute. Wait, 4.18 to 5. Hey, wait, look, 4.2 seconds is in there. So here's what this, again, how a confidence interval can be viewed. We are, in this case, 99% confident that the 0 to 60 miles per hour is, I'm not even sure what they call this thing now, is between 4.18 seconds and 5.77 seconds, which means that, notice, 4.22 seconds is in here. So what this is now, the interpretation of this is that we, our prototype car may meet conditions. So what's going on here? Why is it that one failed and one didn't? So right now we have a mismatch between the two. I mean, I chose a very high confidence level. So what happens when you choose a very high confidence level? Well, what you're doing is you are increasing the ends, right? As the confidence level goes up, so does the margin of error. So I went so high that it encompassed this value. Okay, as a matter of fact, notice that, look at the p-value, 0.0056, and look at this value that I chose, 0.005. The two are actually connected. Okay. So we seems we have a contradiction. What would we need to do here? Well, the engineers would need to go back to the drawing board and maybe we need to determine how accurate we need to make this, because notice this goes from 4.18 seconds to 5.7 seconds. And that is a pretty large margin of error, right? This is a huge margin of error, which means that whoever designed this test didn't really think into account, well, what is the margin of error that we really want? Like, to what level? But this is pretty wide. You know, given what you're trying to show, this is a really, the margin of error is just too wide. So we need to rethink what the sample size needs to be, redo this again. And that's why you always first figure out what the sample size needs to be, which means that you first need to think about what the margin of error needs to be. So anyway, this is kind of an example of what not to do.